All right. So, So welcome back, and what we are continuing today is our discussion and review of feedback amplifiers in order to answer the questions here in front of us, which will Q question 3A and B. Question C we didn't do, but we will still have a look at it when we get it. Basically, to revise sort of just circuit theory, right? So feedback amplifiers, and what we had been doing is looking at the configuration of feedback amplifiers. And let me end the show here, and then we will stop sharing, and we share this now, right? So we saw that there were a number of configurations possible with feedback amplifiers, and the combinations had to do with the names depending on first off what was being fed back, in other words, what was being sensed, which is the first part, and how the feedback was being provided, which was the second part. So there were two types of amplifiers where we sense the voltage outputs, and then there were two types of amplifiers where we sense the current output. And then depending on what we sense, we have to either feed it back in series if it was a current feedback, or if we were feeding it back in voltage, right? So we had all of those configurations, and the configurations were, as we had pointed out in this class here, that there were the feedback now, so the voltage amplifier, and which was the run-of-the-mill everyday voltage amplifier, was at the feedback on that was to give you had to sense voltage and feedback voltage. And then they had the trans-resistance amplifier where you sense voltage but fed back current. The transconductance amplifier where you sensed current and fed back voltage. And then the current amplifier where you sensed current and you fed back current. Okay? And your part of the things that I ask you to sort of memorize, at least unlearn, would be these particular configurations here. If I asked you how to draw a trans-resistance amplifier with feedback, to know the configuration of the trans-resistance amplifier is current in and voltage out. So therefore, if it has feedback, you have to sense voltage and feedback current, right? And then of course, also because of that, to know this, there was a table, or there was a table early on, where the input-output relationships for the various amplifiers were concerned, right? So once we did that now, we said that there were some advantages to be gained by providing feedback, otherwise was a sense of doing it. And among the lists here, the main sort of topics were these, that you can, for the voltage, the amplifiers where the voltage was an input, right, that you increase the input impedance, or you, for those where current was an input, you lower the input impedance. And then the converse, if the output was voltage, you wanted to drop the output impedance. And if the output was current, you wanted to increase the output impedance. Remember again that all devices, if you look at devices here, all devices have an input resistance, well, really an input impedance, but for our cases, we will just model it as a resistor, and an output. Oops, let me put it. So we have an R and an R. The device is somewhere inside of here doing whatever it's doing. So it takes a signal in, and therefore what comes in, regardless of what you're doing inside of here, current has to flow into these devices. So it is always an advantage to have the input impedance as low as possible, so you maximize the current flow into it, right? And therefore maximize the sort of input signal. And then similarly, when you're sending it out, you want to, if you're putting out a voltage, you want most of the voltage to appear across the load, so that you want this to be as low as possible. If you're sending current out, then you want to maximize the amount of current that goes out on that in that direction. All right. So that's what we're trying to do with the feedback here, and we'll see how that's done. And then we'll talk about the gain and the frequency response of it. So without getting into the analysis, if you analyze it from a conceptual basis, if the feedback signal is voltage, right? The feedback signal is series applied, meaning that it's voltage. Then if the feedback, and it's negative feedback as well, right? So since the feedback opposes the input voltage, all right, it means that the current that you're going to get into the input is going to be decreased, because you remember the current is the input resistance divided by the input voltage. So if you do something that effectively reduces the input voltage, the current is going to decrease. So from the source's point of view, it is going to look like the source sees an increase in resistance because the current has fallen, right? And the other way around is that if the feedback is current, then what you're going to do now is that the signal current is going to increase, because you have to supply both the feedback current and the signal and the current going into the device. So if the current increases, the only way that can happen is if you decrease the input impedance, right? So it depends on whether you're feeding back current or voltage. And let's look at the configuration here. The first thing to note is that this now is shorthand for the other circuit that we have. So the voltage series feedback, remember we don't have the feedback network inside of here. This is shorthand for, let me share it, right. That diagram is shorthand for this network, right? So what we've done here is that we, in the diagram that we're looking at, we have, oops, back this up a little bit. Yeah, what we have done in the diagram that we're going to look at is that we have eliminated all of this, right? So we're just dealing with the voltage amplifier and the equivalent circuit, and instead of this, we're going to put a voltage source here, all right? And then you're just going to see that in the circuit going forward, right? So let's get back to our the one that we're interested in, which is this. All right, let's move this. We can share now this. Okay, so what we've done is to eliminate a feedback network, and the feedback network basically is responsible for providing VF. Okay, the other thing is that if you, with all of this inside of here, the source, anytime you're dealing with this, and remember this for other things as well, all this source, all this voltage source here is seeing is what is happening at these 2 points here, okay? In other words, this, for all it cares, this is our wall right here. It can't see anything. All this source knows is that it is a value Vs and a current I in is being taken from it, okay? So therefore, this source, this is almost like if you're in a classroom. So this is a wall, this is another classroom on this side. And in this side, all you have are 2 terminals. They put a voltage source on it. And the voltage source is telling you that, okay, I know what the voltage is and I know what the current is. So as far as the source is concerned, the source is seeing an input impedance given by its own voltage divided by whatever current is taken from it. Fair enough? Right, so we're drawing this for our convenience, but if you put yourself in the position of the source, all the source knows is that its own value is Vs and the current taken from it is I subscript lowercase I, right? I input. So let's see how that helps us inside of here. The source now, if we analyze the circuit, the source doesn't know anything more. But in our case, we know that the source voltage has to be equal to the, there are 2 things happening inside of it. There's a feedback voltage, right? There's a feedback voltage Vf here. And there is some voltage developing across the input impedance of the amplifier. So if we were to equate it, V source, simple circuit here, is Vf plus Vi. We know that Vf is the feedback coming from the feedback network, whose gain is beta V out. And this voltage here is just simply I in by R. Okay? So we have this particular bit here. The other part of it, and if you want to, let me just put a little side here. RIF is equal to Vs over I input, right? This is what the source is seeing, right? Okay. Vs is this bit here, right? So if I want, I could substitute that inside of here. So I have beta V out plus I input, R input over I input. Yeah? So I could cancel that a little bit. And what I will get, but this will cancel here if I were to divide it out, is beta V out over I in, right? Plus R in. Fair enough? And what is V out over I in? V out over I in is what? Right, we have V out and we have I in. So we have to now substitute back inside of here. We have a relationship here between V out and I in. Okay, V out is AV, right, as a voltage gain, AV by V in, right? And then in terms of the output resistance and so on. So you can get a AV by V, V out is AV VI, which is VI is I in by R in. So you can make the substitutions inside of here. And then once you put it out, remember this is a voltage gain inside of here. So once you put it out and substitute now into everything, what you end up getting, if you simplify it, this is just, you don't really need this too much, is that Vs over I in which is the input impedance that I have here, right? This Vs over In, right? Turns out to be the input impedance Ri into 1 plus beta AV. Fair enough? It's just a question of substituting. But the important thing here now is that look at what has happened. The input with feedback, remember the original input as far as the circuit was concerned, the original input impedance is Ri. This is inside of the circuit. By providing feedback now, we have the input we have the original input impedance, but we have a beta times the voltage gain. And remember, the voltage gain is greater than 1, significantly greater than 1. So, and beta, usually the feedback factor is more than 1. So the input impedance now has now been increased by a factor of beta AV. So in other words, for the voltage series feedback, which is what we're saying, that the input impedance has now been increased. And we conceptually said it before, because this voltage is opposing this one as far as the source is concerned, right? If I am putting a voltage here and a current is supposed to be leaving me, but inside, behind this barrier, as far as the source is concerned, there's another voltage opposing this. So in other words, the current here is going to drop. So as far as I am concerned, if this goes down, then our IF is going to go up. And how much this goes down is by the factor is related to the gain of the circuit. All right? Yeah? Make sense? No, maybe?
Yeah.
All right? Conceptually, we understand what happens. The rest is just to use what we know already. And as I say, if you put yourself at the source and all the source is seeing is a current going and it knows its value, then we can say our issue is to determine really what the current is, because we already know what Vs is. So what is the current? The current has been reduced, and we have to figure out how much the current is reduced by. Yeah? In the case, and there you have it, so the impedance is reduced by that amount for voltage series feedback. The other type of, where are we? Which one is the, right, the other one, the transconductance amplifier is the other one that has a series feedback in it, right? This one, because it's a series feedback, the transconductance amplifier, remember, the voltage in, current out. So you're feeding back voltage like the voltage amplifier. And because again, the source impedance, the source, sorry, is only seeing voltage and a current going this way, because we are opposing the source voltage, the current is going to drop. So for this kind, again, this is another series feedback, the input impedance is going to increase as well. And if you do the calculation, you see that for this one, the input impedance increases by the GM factor. Remember, the GM factor is the transconductance of this, which is the output current over the input voltage. All right? In other words, it's just as an aside, the transconductance right is also known as a voltage controlled current source. So you control, remember the transconductance amplifier is current output and voltage in. So depending on the voltage that you put in, you get a certain amount of current coming out, right? So you'll also see this in books and in articles as well, that sometimes they will call it a transconductance amplifier. Sometimes they also call it a voltage controlled current source. Okay, so you're controlling how much current you're getting out by the amount of voltage that you put in. In both cases, the input parameter is voltage. So in this case, in both this and in the voltage amplifier, the input impedance is improved by the feedback. The current amplifier now, right, or let's look at the other amplifiers, the feedback current, which are the voltage shunt, right, and the current shunt. Sorry, not this one, the current shunt, right. So in both cases now, let's go back here, the voltage shunt feedback is, this now is a, let me get back to the first, right, is a transresistance amplifier. Transresistance means we're sending a current in and we're getting a voltage coming out. All right. And if you like, this is a current control voltage source, but that particular term is not used too common. So in this case, the source, again, this is the source, and the source is seeing, all the source knows is that it's supposed to be supplying a current. And in the case of the feedback that we're doing here, the current is such that the feedback current is negative feedback, so that whatever source current is supplied has to supply both the input current and the feedback current. So because of that, the source has to supply more current when you put feedback in it. So therefore, if I'm supplying more current, as far as I'm concerned, the input resistance has dropped. Okay, and the proof is the simple analysis again, that input impedance, it always comes back down to this, that the input impedance is Vn over the current, and then we can work the math just that we did before, except that we're working with currents this time. So once you're dealing with shunts, shunts have this arrangement, the shunt feedback, all of the shunt feedback amplifiers, which is the transresistance, and the current amplifier, both of these, the input is current. So once the input is current, it means that the feedback has to be current, meaning that the feedback has to be in shunt or in parallel with it. And the source will have to supply the original input current, which was the current without feedback, and whatever the feedback is asking it to do. So the source has to supply more current. So if this goes up, right, it means that as far as it's concerned, the resistance value will go down. And the calculation here is, again, everything that we know about the relationship between the input and output. Okay, so just a question of substituting, but here you have the final answer here. Rm, in this case, Rm is the transresistance of the amplifier, right? Which is what do you call it? I out over Vn, right? Okay, that was a definition. That was a definition here, right? That we did from before, and of course the current amplifier, right? Which is the last one, right? The current amplifiers, you're sensing current on the output and you're feeding back current on the input. And we said this kind of amplifier, a very simple example of this was the pass transistor in the regulated power supply. But because it's a shunt feedback, the same thing happens here, right? The source has to supply both the feedback current and the input current, the original input current. So because it has to supply more, this goes up, so therefore the effective input impedance goes down. And in this case, it goes down by the factor of the beta times the current gain of this. The input current, the output current divided by the input current here. Right? So all of these, once you get the first thing is that any question that is asked. So if you ask a question, okay, show that what is the change of input impedance for a voltage shunt feedback amplifier, voltage shunt, right? Voltage shunt amplifier. From the time you see shunt, it means that what it is that first off, you're detecting voltage on the output, but you're feeding back current, right? So what kind of amplifier has a voltage on the output and feeds back current? Voltage on the output, so it's feeding back current, which means that the input is current and the output is voltage. So if the input is current and the output is voltage, that is your transresistance, transconductance amplifier here. Transresistance, sorry, my miss transresistance, right? Right, current on the output, current on the input, voltage on the output. All right?
So the big rectangle represents how the left side of the circuit connected to the right side of the circuit.
Right. This is the equivalent circuit. The rectangle is the equivalent circuit. Right? So as far as this, like the voltage series amplifier, right? The voltage series amplifier is that you have you have an input impedance, the output impedance, the voltage series amplifier, the gain of the voltage, so because it's voltage series, voltage input, voltage output, right? So there's a voltage amplifier. So this equivalent circuit of it is that you have a voltage in, there's an input impedance, the amplifier provides a voltage gain of AV type VI, so that the equivalent circuit output, remember there's a Thevenin equivalent that we're talking about, is an output voltage source now in series with an output impedance. All right? In terms of the voltage shunt amplifier is a current, the transresistance. So you're dealing with an input current coming here, and the output now is a voltage because of transresistance. So it's voltage out and current in. So that what the circuitry is doing is taking an input current and giving you an output voltage. So the Thevenin equivalent is our output voltage source. The voltage source value is RMI, and of course a voltage in series with a what do you call it? A resistance. Yeah. You have two types of, remember, the Thevenin sources are a voltage source in series, right? Some voltage in series with a resistance. And the Norton, what do you call it? The Norton type are current sources in parallel, so an I in parallel with an impedance, right? Those are the equivalents. You would have learned that in circuit theory way back. It's just a way of summarizing the behavior of the entire circuit in shorthand. All right, and all of this, all of these values here are what was in the very first table where we spoke about the different types of amplifiers, and we summarize what the gains were, right? What the input-output relationship was, right? So the voltage amplifier is AVVN, right? the trans resistance is Rm In. The transconductance is GMVI, and notice that the output is a current source, and the current amplifier, of course, is AI by I, and it's a current source in parallel with an impedance, right? So this is really just shorthand. All of this is just really supposed to be shorthand, right, for describing that circuit, like this circuit that we had here. Let me go back to the beginning, right? So a circuit like this with voltage shunt or voltage series feedback, instead of having this and trying to figure out what it is, we replace all of this, right, by the equivalent, by this instead, right? So all of that circuitry has been replaced by this rectangle here. Oops. Yeah.
Oh, I know, see.
Right. Right. Is inconvenient. We could not make that sort of analysis if I was using this. Right. This is a circuit design that happens to be voltage series feedback, but it's too hard to analyze that looking at it here. So what we do is that we replace all the circuitry by a block, and the block has three components in them: an input impedance, although we're showing it as a resistance here, an input impedance, an output impedance, and whatever is the input-output relationship for the particular device, right? So that changes here a little bit. So if the input-output relationship is voltage, then you're going to have a voltage source. You're going to have a voltage source here. If the input-output relationship is current, then you're going to have a current source instead. Yeah?
Yeah.
Okay, good. All right, so that was input impedance, right? So the feedback, depending, if you have input amplifiers that have voltage, you increase the input impedance. If you have amplifiers that have currents as input, you want to decrease the input impedance. The output impedance approach is a similar sort of thing. This one, and you do this like when, again, you were analyzing your, there we go. Right? When you were doing a circuit theory and you were given a little network and asked to find what is the Thevenin equivalent of it, you have to do things like set all the current sources, set all the voltage sources to open circuit, the current sources to shorts and the like. Okay, so you could figure it out. Right. So it changes the input impedance. Feedback has an effect on input impedance. Feedback has an effect on output impedance as well. All right, and it depends on how the feedback, how the output is sampled. Right. So as we say in this one now, if the feedback, if we sample an output voltage, all right, then no matter how we feed it back, because this is the output stage that we're looking at. If we sample the output voltage, the output impedance or resistance is reduced. And if we sample the output current, then the output impedance is increased. Right? And to prove it now, we have to do certain things. This one is a little bit different because what we're looking at now is we're trying to look at it now from this side. Right? So what is the output impedance of this device? To calculate the output impedance of a circuit, you need to set the voltage sources to 0, right? So any source voltage, you set to 0, and then you remove the load. We don't want the load in the circuit. We're looking to see what is happening here. So we don't want the load in the circuit as yet. Okay? So you said you remove the output source, and the only way to find out anything, if I give you a black box, if I give you a black box in the lab with 2 terminals, and I tell you what is the input, what is the resistance of that box, you don't know whether it's an output or an input. All you know is that to find resistance, I put a voltage across here, and I measure the current through here. And that will tell me from these two terminals, what is the resistance between these two terminals. So it's the same sort of thing here. If you take this box, take all of this thing as having two terminals here and here, right? We know on this side, and I want to find out what is the resistance looking this way, then I have to put a voltage here. I have to put a voltage across here and measure the current going in, and then see what happens. But of course, I can't have this circuit powered so that I have to remove, sorry, not I can't have other inputs affecting me. So I have to make sure I have no other inputs around. So I have to get rid of the voltage source, right? So make sure the voltage source is 0, right? So the voltage source here is 0, meaning that we are basically short out there. That doesn't exist anymore. And then we now look and see what happens with V out over I. All right? And here you have it. So if Vs is 0 for this particular one, remember this one now is irrespective of this part. So this bit doesn't think. We're now looking at the thing that we're sensing. So Vs is 0 and the analysis. So if Vs is 0, it means that V in is equal to minus Vf, and Vf is my feedback voltage is minus beta V, because I've put a voltage on the, this is what is being fed back, right? The feedback network will be taking this, right? So we have V here. I'm putting V on the circuit, so V is being fed back. So Vf is minus and is negative feedback, so it's minus beta V, right? And then I in, we know that for this particular, the voltage circuit here, that if I have, what do you call it, the input current here is this, well, this minus AV, and by whatever is the output impedance of the amplifier here. So if I make this substitution now, what I get is that the output impedance has been decreased by the value of beta AV. So as far as this is concerned, once I have voltage feedback, the output impedance is dropping. And then the last thing to do is to push back, to put back in my load. And the load is now in parallel. Remember, ROF, if you get rid of all of this thing, ROF is really right here. Okay? So if ROF is this bit here, then once I put back my load, the overall output impedance now is ROF in parallel with RL, which is this. Okay? And if you parallel two resistances, the value of this means that the equivalent load, it also drops. This is going to be less than RL, right? Or whichever is the smaller one is going to be the smaller than that, all right? Make sense? Simple circuit analysis here, once you remember how the circuits are configured. So the output resistance for voltage series feedback, and then similarly, the current, once you're feeding back, once you're sensing current, right? Once you're sensing current, the output impedance goes up, all right? So anything with voltage feedback, the output impedance goes down, and anything with current feedback, the output impedance goes up. Yeah? We all right on that? And then, right, getting back, so let's kind of review the question, didn't deal with that, but other questions me. And then this other bit now, we know that in the feedback remember we have the block A, oops, and we have the feedback beta. Right? So we know that the transfer function with feedback, right, which is what we trying to see what the effect is A over 1 plus beta times A. Now, if this factor beta A is much greater than 1, in other words, much greater than this, then this whole expression really reduces to A over 1 plus A beta. The A's cancel, so the gain, the closed loop gain, right? Remember, AF is a closed loop gain, that is a gain with feedback, is 1 over beta. Notice that it is independent of the open loop gain A. All right, and remember what we said, the open loop gain is susceptible to things like temperature change, component value changes, etc. But notice that by supplying feedback, that A could change within reason, A could change however it wants, but the feedback of the overall, the gain of the overall system is independent of that. It only depends on the gain of the feedback network. All right, which is a marvelous thing. And this usually is just some resistors and so on if we have in the feedback network. So what we've done is to try to make by providing feedback, that we make the gain of the amplifier almost immune to changes in A. So it could fluctuate up and down with temperature a little bit and so on. There's a limit to it, and we're not looking at that right now. But in conceptually, if everything behaves within reason, that the closed loop gain is immune to the changes in the open loop gain. All right. And then the last thing is, what about feedback? Sorry, what about the bandwidth? If you have an amplifier and the gain is given, just for argument's sake, we have an amplifier and we know this sort of expression from our signals and system. This is a simple one pole transfer function, right? So this is a K over S plus K over S plus A type transfer function, a single pole, no zeros, right? So if I, and we know, if I ask you to plot to do the Bode plot, if I were to give you that AS is equal to something like this, then you take the substitution S equal to J omega, right? And then you express it in the standard form that we have here. So you know now that if I were to ask you to draw the frequency response for this, this has a corner frequency at omega 0. So that the frequency response of it in decibels will be 20 log K, whatever that is. So let's say it's 20 log K. And then for this bit here, we have that it will do this and then roll off at minus 20 dB per decade. So that the overall response for something like this would look would look like it would go up to here, and then from this point down, it's decreasing at minus 20 dB per decade. Yeah, this is overall. This is 20 log K here. Right, so that's the frequency response. So let's see now if we put feedback onto this. So AS is that original expression here. With feedback, it is the transfer function with feedback is now AS over 1 plus beta, and we substitute the AS that we had before, right? So we've gone from here, and we want to find out AF of j omega. We have to substitute j omega into what we have. So A of j omega and 1 plus beta, A of j omega, which is this bit that we had in the previous slide, right? Juggle it around a little bit and do some grouping now. So when I have it in this form, what I do, I divide it through by 1 plus beta k to get it into the sort of conventional form that we want. Notice now that if we draw the board plot now, all right, let me get back the font color here. All right, this bit now is 20 log of k divided by something. So this is a little bit, the original 20 log k would be here, right? This was 20 log k, which is what we had before, right? 20 log k. This now I'm dividing by k over 1 plus beta k. So this is less. So if I draw this particular one is going to be something a little bit less now. All right. And then what has happened here now? Omega, instead of the corner frequency at omega naught, all right, the original corner frequency was at omega naught. Instead, now the corner frequency is omega naught into 1 plus beta k. This is a bigger number. So the new corner frequency is now somewhere here, right? Let me call this omega naught prime is equal to omega naught into 1 plus beta k, right? So this is omega naught prime. So the gain has fallen, but the corner frequency has gone up, so that the response for the pole is now looking like this. Just, excuse me a second. Yeah. So that the corner frequency has now gone up, so that the overall response is now going to look, let me put it in red. The overall response now with feedback is now going to look like this. Right, of course, this is a minus 20 dB per decade. So if you compare that with what went before, the gain has dropped, but the bandwidth has gone up. So in other words, the providing feedback, right, increased the amplifier bandwidth by a factor of 1 plus beta k, and has decreased the open loop gain a bit by a factor of 1 plus beta k. So you're getting there's an advantage and a little bit of a disadvantage here. One, you're getting a wider bandwidth, which is good by providing feedback. Remember, the bandwidth of these circuits are important. but you have to, the gain is dropping a little bit. But you could compensate for that. Gain is an easy thing to compensate for. You just increase the open loop gain a bit, so that by the time you provide feedback with it and it decreases, it comes back to the sort of level that you wanted. Yeah. So we've now covered what we need to go and answer the question that was here. So what is meant by gain stability and why is it important in the design of such amplifiers? Right. So the answer to that, of course, gain stability is the variation of the amplifier gain A with the variation of A with the component parameters, the variation of temperature and component values and so on. So the answer for this will be by providing negative feedback, the amplifier provides, if the feedback factor beta is greater than A, then what happens is that the negative feedback amplifier, the gain of the amplifier is independent of the open loop gain. So in other words, the gain is stable, right? And you prove it by the little explanation that we had in the slide before that. You show that if the feedback gain is A over 1 plus A beta, right? If A beta is greater than 1, then this is essentially A over A beta, which is 1 over beta, right? So that the feedback, negative feedback amplifier, the overall gain now is independent of A. So therefore you have the gain being stable in that it does not depend on this any longer. All right. And then the other part here now, you have an amplifier with an open loop gain given by this, where A is a low frequency and F is the open loop bandwidth. Show that the bandwidth of the amplifier is increased by a factor of the open loop gain relative to the bandwidth. So you can use F or you can use omega, right? It doesn't matter. This was an older paper, so normally I would give you it in terms of omega, but it's the same thing. Omega and F, omega is 2 pi F, so it's the same sort of arrangement. So what you do again is that you show this is the gain, right? But instead of here now, the gain of the A open loop now will be the A over 1 plus J omega over omega naught, and you substitute it into here, and then when you group it together as you were as we just saw, to draw the board plot for it, you would see that now that the gain now has been increased by a factor down here, that omega naught is now omega naught plus a beta omega naught inside of here, right? So that once you do that now, you can show and you draw, and of course you answer it by showing that, and then you could draw a simple plot to show the original. So you could draw and say the original response would have looked like that, and now the original response looks like that. Remember that the gain drops, but the bandwidth increases. Yeah. And of course, if you're plotting it, remember to put this as minus 20 dB per decade. Yeah.
So the omega and that F, different, or it is the same?
No. You remember omega naught is 2 pi F naught, right? So if I have 1 plus J omega, let's say I have a J omega over omega naught. Yeah, I could convert that to frequency, that is J 2 pi F over 2 pi F naught, right? Which is JF over F naught, right? So this is just another way. You could express it in omega, or you could express it in F, right? Remember, and this is the relationship between omega This is in radians, this is in hertz, but it's the same radians per second and in hertz. Right, but it doesn't make a difference. A more general form for expressing it in the Bode plot form is to use omega rather than f. But as you can see, if you substitute 2 pi f and 2 pi f naught, the 2 pi is cancelled, so you get the same relationship that we were talking about from before. Yeah. Make sense?
Yeah.
All right. So that takes care of question 3. The other part, where's the diagram? I didn't print out the diagram here, but we look at the diagram after we finish this and just see as a circuit theory bit of revision to look at the diagram and see what it's about. All right. And we, in terms of question 4, we actually did this, but we'll go over it. The one that we did in December had the diodes reversed, right? So this is another variation. In December, we had the diodes this way, all right? So the operation is similar, but the polarity will be reversed. But we will talk about these a little bit more. And then this one is a waveform generator. This is a triangle waveform generator. So we'll talk a little bit about those. Just review the waveform generators and the precision rectifiers just briefly on Friday now, right? So a lot of stuff again we've covered. Again, we covered a chunk of, just in doing this question, we looked at the whole question of feedback amplifiers, the configuration of the feedback amplifier, or the topology, I should say. Right, the topology of the feedback amplifiers, the various types, the input-output relationships, and the fact that once you supply negative feedback, and the feedback amplifiers here are all negative feedback amplifiers, right? Once you provide negative feedback amplifiers, there are a number of things that are improved, a number of the characteristics of the amplifiers that are improved by providing the feedback. All right. If you make the mistake and put positive feedback, then a positive feedback amplifier creates an oscillator. Right. And we discussed those as well. Right. This is deliberate. You deliberately put positive feedback. You would not want to put positive feedback on a normal, like an audio amplifier or an amplifier to drive a motor or something of that nature. All right, you're looking for trouble there. But you may want to, if you want to create something like an oscillator, then we put the feedback as positive on that. All right. So any questions before I stop today's class?
So the plots that you draw, how you came up with that?
Which plots?
From the previous slide.
Yes.
Yeah, that one. Like
these were actually I just drew on the on what we Bode plots from signals and systems. Remember, we just reviewed that. If you have a single pole system, right, and I think we may be coming to that in signals as well. But if you remember, if I ask you to draw the frequency response of a single pole system, you substitute S equal to j omega. So the first step will be to get j omega plus A, and then we get it into a constant form, right? Which is to express it in the form of K over 1 plus, in this case, j omega over A, right? So you express it in that form at K over A. You divide through by A. Let me just, where's my pen? K over A. And then we went through in the Bode plot thing, this is ECNG 2011, how to go from here to these diagrams. So that is something you're probably going to have to look at, is the Bode plots. right? We have 3 lectures on that. So look for board plots 1, 2, and 3. The slides for that and the videos for that. It will explain how we went about doing this.
Okay.
All right. Okay. Okay, folks. So well, tomorrow is a holiday. We don't have classes. We wouldn't have class on Monday, but we will have a class on Friday to finish off this, and then I will tell you what next we're going to do the following week. Okay.